Now that we know how to use ice tables to solve equilibrium problems, let's look at an approximation that's going to make our life much easier for a lot of these problems. So I've started to set up a problem here, and I've skipped a few steps ahead because we should know how to do all of this. Consider the following reaction. If we start with 1 molar of A, what are A and B at equilibrium? So this would be our given information. We always start the same way. We say, okay, first step, I'm going to write my expression. Second step, I'm going to plug in what I know. I know K, but I don't know A and B at equilibrium. I don't know those. So since I have more than one thing I don't know, the next thing I do is make my ice table. So all I knew to begin with is that I started with 1 molar of A and no B. No other information, so I do my usual thing. Okay, there's a 1 next to A, so minus 1x. There's a 2 next to B, so plus 2x, and then I get these equilibrium values. I say, okay, if I look at any given column, there's always x's in 2 rows. There's no way I can solve for x right away, so I'm just going to take my equilibrium values and plug them into k. Now that I have k, I say, this looks like a long algebra problem. I better start multiplying out, rearranging, and everything else. But I can actually take a little itty-bitty shortcut here. What I can do is look at the value of this equilibrium constant. It's really small, 2.2 times 10 to the negative third. And if I have a very small equilibrium constant, that means I'm going to make very few products. And what that means is x is going to be a very small number. So I'm going to make very few products. X is going to be really tiny. And if I look at this expression here and think about it, when you add or subtract a really small number to a value, it really doesn't change it very much. So I always like the analogy, if I have a gallon of water and I add 1 drop of water, I still just refer to it a gallon, not as a gallon in 1 drop, because that 1 drop is so small compared to how much I had. So whenever you have a very tiny number, every time you add and subtract it, you can kind of ignore it. It's not really going to make a big difference. Now multiplying, that's a different ballgame. Multiplying by a multiplying by a very small number makes a really big difference. But adding and subtracting does not. So what I can do, if k is really small, which leads me to believe that x is very small, I can basically just cross it out everywhere that I've added or subtracted in my expression. Can't do it for multiplication, but adding or subtracting because it's small. So I write out x is small and I cross out wherever I've added and subtracted. And now this problem looks a lot simpler. I have 2x squared over 1. All right, now I can definitely solve this algebra problem. So if we scroll down, give us a little bit more room. That's what we have there. So we'll just move this guy over here. So 2.2 times 10 to the negative 3 is equal to 2x squared over 1. Well, first of all, anything divided by 1 is just itself, so we don't really have to worry about that guy. So we can distribute this squared. So I have 2.2 times 10 to the negative third is equal to 4x squared. So I'm going to divide both sides by 4, which will cancel this guy here. And then to get x, I'm just going to take whatever this number is and square root that guy. So ultimately all of x is equal to 0.023, just by plugging this guy into my calculator. And not surprisingly, it's a really tiny number. And so what I can do is I can just go back and plug this in to my equilibrium row. So in this case, a, which was 1 minus x, is going to be equal to 0.0. Nope, what am I doing? 1 minus 0.023, which is going to give me 0.977. B is going to be equal to 2x. Again, I'm just getting that from my equilibrium row up here. So that's going to be 2 times 0.023, which is going to give me 0.046. And now that we're back to talking about concentrations, we'll put our units back on there, which would be molarity. And if I'm being precise with my sig figs, I see that I only had 2 decimals here, so really that would be my last sig fig here. That was so much easier than going through all that quadratic equation nonsense by using this x is small approximation. Again, k is small, that means x is small, so we can use this approximation. Now at the end, you always have to check that you are okay to use the approximation. It's not always valid. And what we usually use is what's called the 5% rule. If x is less than 5% of your initial concentration, in this case 1, then your approximation was valid. So all we have to do is take x, which is 0.023, and put it over my initial concentration, in this case 1, and then because it's a percentage, we multiply it by 100. In this case, we find it's 2.3%. So that's less than 5, which is my threshold, so check. So I always want to do this 5% check to make sure my approximation was good and that I know these numbers are accurate. If this was bigger than 5%, I'd have to go back and solve the long way. But in a lot of cases, when you have these tiny k's, it's definitely worth your while to use this x is small approximation.